Lab 4, Spring Oscillations, featuring Newton's second law and the energy principle. The purpose of this lab was to use Newton's second law to model the motion of a spring mass system in which the mass swings in an arc while oscillating vertically, and to use the energy principle to analyze energy conversions causing this modeled motion. To do this, I first used the program tracker to obtain real position and time data. I then used VIDLE to model the motion and energy conversions. Lastly, I compared the motion predictions to the real data to evaluate the accuracy of the model. The model predicted the x position accurately, but failed to predict the y position in the middle of the time interval. The first fundamental principle used was Newton's second law, which says that net force equals mass times change in velocity divided by change in time. The term net force refers to all pushes and pulls on the system, which includes the spring force and the force of gravity in this case. The gravitational force equals mass times Earth's gravitational constant g and acts in the negative y direction in this case. The spring force equals the spring stiffness constant k times x, the difference between the length of the spring and its relaxed length. In order to predict the motion future of the mass of the system, I used iteration of Newton's second law. I rearranged the terms to give final velocity equals initial velocity plus net force divided by mass times change in time. Updating the velocity allows us to also update the position at each time step using this equation. Final position equals initial position plus velocity times change in time. At each time step, the net force, velocity, and position are updated to give a complete picture of the motion. The second fundamental principle used was the energy principle, which states that change in energy of a system is equal to work done by the surroundings on the system. In our case, three types of energies make up the total energy E: kinetic energy of the mass, K, gravitational potential energy, UG, and potential energy of the spring, US. Taking the mass, spring, and Earth as the system, there's nothing left in the surroundings to transfer energy into the system, and thus total change in energy equals zero. This means that while energy can be converted between these three forms, it cannot be lost from the system to the surroundings. Change in kinetic energy K equals final K minus initial K, where K equals 1/2 mass times velocity squared. Similarly, change in gravitational potential energy UG equals final UG minus initial UG, where UG equals mass times Earth's gravitational constant g times the vertical y position of the mass. Lastly, change in spring potential energy US equals final US minus initial US, where US equals 1/2 times the spring stiffness K times the stretch from relaxed length squared. I put the origin of the axis at the attachment point and calibrated this distance to be 0.7 meters as given in lecture. I analyzed the motion from the time it is released until the end of the video for a total of 98 frames. I identified the center of the mass in each frame to obtain real position and time data. Here the x position is plotted as a function of time, and here the y position is plotted as a function of time. Before we can look at the code, a few more initial conditions must be determined, such as the period of oscillation. The period is the time from one complete cycle of oscillation, which can be determined from this plot. The time between each trough of this plot is exactly 1.52 seconds. We can then use this information to determine the spring stiffness constant K for this particular spring using this equation, and we find that K equals 10.441 newtons per meter. Lastly, we need to find the relaxed length of the spring. We can do this because when the spring is vertical, we know that the magnitude of the force of gravity equals the magnitude of the spring force. We also know that at this time, the stretch length of the spring is 0.7 meters. Thus, we have all variables needed to solve for the relaxed length of the spring and find that it is 0.323 meters. Now we can look at the code. Here I put in the mass, initial position from tracker, initial velocity, and starting times. I also put in the time step delta t, keeping it small relative to total observation time in order to get many position updates and make my estimates very accurate. I also initialized the gravitational constant, spring stiffness, relative length of the spring, and length and orientation of the spring. Here I inputted the energy equations previously discussed: kinetic energy, gravitational potential energy, and spring potential energy. Next we enter the calculation loop applying Newton's second law and the energy principle. Here I have the length of the total time interval, gravitational force, spring force, net force as gravitational plus spring, Newton's second law, and the position update equation. Here the spring and mass are updated to the position calculated. Then I calculated the new kinetic energy and change in kinetic energy, new gravitational potential energy and change in gravitational potential energy, and new spring potential energy and change in spring potential energy. To analyze this information, I plotted the change in kinetic energy in blue, change in spring potential energy in red, change in gravitational potential energy in green, and total potential energy in yellow. When I run the code, here's what I get. A blue arrow represents spring force, black arrow represents gravitational force, and yellow arrow represents net force. The gravitational force nearly completely balances the spring force, so the net force arrow is weighted 7 times that of the other two forces, with an arrow scale of 0.35 rather than the 0.05 of its components. Based on the energy graph, you can see that the change in spring potential energy in red appears to be equal and opposite of gravitational potential energy change in green, and the kinetic energy change in blue oscillates much more quickly, seeming to balance with itself. The total energy change in yellow appears to be very close to the expected value of 0 and deviates from 0 only slightly at points. In order to make comparisons with the actual data, here I imported the x and y coordinates from a file containing the data from tracker and added a red ball visual to mark the actual position of the ball throughout the model. I also plotted the model and experimental x coordinates and model and experimental y coordinates to get a sense of the accuracy of the model. Here's how it looks. Note that the red ball appears jerky because there are 10 data points of the blue ball before the red ball is updated by 1 position point, as reflected by my choice of time step to be 1/10 of the number of frames per second. You can see that my X position in red and blue match very closely, but my model largely fails to accurately predict the Y position. This is likely due to additional interactions from the surroundings, such as drag force, which was not accounted for in our model. What does it mean, number 1? For this model system, is the energy principle satisfied? Based on this plot, total change in energy is not exactly zero, which would lead us to believe that the energy principle is not satisfied, or there is an interaction we did not account for in the model. However, most of the deviation from zero can likely be attributed to accumulated rounding in the code, and for this reason, I believe the energy principle is satisfied. What does it mean, number 2? Determine the period of oscillation from the Y position data and X position data. Compare and discuss these values. I previously discussed the period obtained from the Y position data was 1.52 seconds, which was the amount of time between each trough in the data. Using the same procedure for the X position data, we find variable distances between troughs and an average of 1.64 seconds. The period found using the Y position data accounts for a vertical oscillation of the spring, while the X position data shows horizontal swinging of the mass. In my experiment, it took longer for the mass to swing horizontally back to its starting X coordinate than to oscillate vertically back to its original Y coordinate. The swinging motion was also more variable than the oscillating motion.